Hi everyone. In these videos, we're going to be talking about discrete random variables and their probability distributions. We'll start off by looking at probability models that are created using tables, and then we'll talk about a very special probability model called the binomial model. So first, what is a random variable? A random variable is a numerical outcome of a probability experiment. So, for example, probability experiment is rolling a die or flipping a coin. But when we roll a die, we're going to get outcomes like 1, 2, 3, 4, 5, or 6. Those are numerical outcomes, whereas flipping a coin, we're going to get heads or tails. So the random variable are the numerical outcomes of certain probability experiments. We have two types of random variables, discrete random variables and continuous random variables. We talked a little bit about the difference between discrete and continuous in Chapter 1 when we talked about variables. Discrete means that the variable is countable. The outcomes are countable. They're whole numbers, like 1, 2, 3, 4, 5, or 6. Whereas continuous means that the outcome can be any value in an interval, including decimals, fractions, and so on. So rolling a die is or the number that comes up is an example of a discrete random variable because you're never going to roll a die and get 2.5. Also, the number of siblings that somebody has, right? We can't have half a person. So those are discrete random variables. Continuous random variable could be the height of a randomly chosen student, right? Heights can have fractions to them. Same thing with the amount of electricity used. So we want to create a probability model for a discrete random variable. And in the beginning here, we're going to do this by creating tables. Because they're discrete random variables, they'll have those countable outcomes. It's easy to put those countable outcomes into a table like this, and then have their associated probabilities next to them. So for example, we have 4 patients that have made appointments to have their blood pressure checked at a clinic. We're going to let X be the number of them that have high blood pressure. Use the probability distribution of X to the right to calculate. So let's look at what this model is saying. So X then is the number of patients out of 4 of them who have high blood pressure. So we really have a limited possibilities here. Either 0 of them have high blood pressure, exactly 1, exactly 2, exactly 3, or exactly all 4 of them have high blood pressure. And then we have the probability associated with each of these outcomes. So if we're asked to find the probability that X is greater than 2, this is saying what is the probability that more than 2 of these patients have high blood pressure? Because this is a discrete variable, then more than 2 means 3 or 4, right? Because we can't have 2.5. So the probability of more than 2 in this case would be the probability that X equals 3, or, so I'm adding, the probability that X equals 4. And then we're literally just adding those probabilities together. The probability that there are 3 patients with high blood pressure is 0.08, and the probability that there are all 4 patients have high blood pressure is 0.01. We add those together to get our answer, 0.09. In Part B, it asks for the probability that at least one of these patients has high blood pressure. Well, at least one means 1, 2, 3, or 4. So we could add those together, the probability that one patient has high blood pressure plus the probability that 2 patients have high blood pressure plus the probability that 3 patients have high blood pressure plus the probability that 4 patients have high blood pressure. Or we can use our complement knowing that if at least one includes all 4 of these outcomes, then the complement of those 4 outcomes is this one. So we can take 1 minus the probability that none of the patients have high blood pressure. and therefore we can just take the 0.23 and subtract it from 1. When looking at this probability model, we always want to talk about whether or not our table is a valid model. So when we talk about valid probability tables, it means that every probability that's listed is between 0 and 1. That's what this says here. So all of these values have to be between 0 and 1. And also, this has to include every possible outcome. So therefore, these probabilities should add up to 1. So this says the sum of all of the probabilities should equal 1 exactly. And if you were to add up all of these probabilities here, you will get 1 as your answer. So again, I have the properties for determining if a probability model is valid. And we want to look at these 3 models here and see whether or not they're valid. So looking at this first one, you can see that when x equals 0, it's saying the probability is negative. That can't be. Oops, wrong way. There we go. We can't have a negative probability. So this is not a valid probability table. For the next one, all the probabilities are between 0 and 1, but if we were to add these up, we're going to get some value greater than 1. And therefore, this is not a valid probability table. Remember that they have to add up to exactly 1. This last probability table is valid. All of these probabilities are between 0 and 1, and if you add them up, you will get exactly 1. It's okay if the x values are negative, but the probabilities have to be a positive value between 0 and 1. So this is a valid probability table. When we have created a valid probability table, a lot of times the next question is, what is the expected value? Another word for the expected value is the mean, but it's not just the mean of the x values, it's the mean of the x values that's weighted according to their probability. And so we call it an expected value. So it's really a weighted average. We find this by taking each x and multiplying it by its probability and then adding all of those up. Sometimes when we have a really small table, like the example I'm about to do, we can do this by hand. But I'm also going to show you how to use the commands in your calculator to find this as well. So in this example, we have that Mary is deciding whether to book the cheaper flight home from college after her final exams, but she's unsure when her last exam will be. She thinks that there's only a 20% chance that the exam will be scheduled after the last day she can get a seat on the cheaper flight. If it is, and she must cancel the flight, she will lose $250. If she can take the cheaper flight, she will save $100. We want to create a valid probability table and then find the expected value and interpret it in the problem. So we have 2 things happening here. Either she's going to be able to book the cheaper flight and keep it and save some money, or she's going to book the cheaper flight, need to cancel it because she has to take her final exam, and then lose money. So for the outcomes, she has either that she's going to cancel that flight or keep that cheaper flight. If she cancels the flight, she's going to lose $250. So the outcome or the payout is negative $250. But if she can keep the cheaper flight, she's going to save $100. So now the X value is positive. The probability that she needs to cancel the flight, it says 20%. So we write that as 0.20. Remember that a probability table has to add up to 1. So if there's a 20% chance that she's going to cancel the flight, then there's an 80% chance that she's going to be able to keep the flight. So now we have a valid probability table and we want to find the expected value. So we're going to take each of the x values and multiply them by their corresponding probabilities, and then add those values up. So we're going to take negative 250 times 0.2 and add it to 100 times 0.8. And we get an expected value of $30. What does this mean? Well, first, it means that she's expected to save money. So that's good. But notice that in her circumstance, it's either one or the other. She's either going to lose $250 or make $100. In none of these instances is she actually going to make $30. What the expected value says is that if she were to be in this circumstance many times and either keep the cheaper flight or cancel the flight and do this again many times, that overall she will come out ahead with $30. But with each individual trial, she's either going to lose $250 or gain $100. So basically it says that if she does book the cheaper flight, she can expect to gain $30 on average, right? Meaning that she does this quote-unquote trial many times. Then on average, she will expect to gain $30. So we also like to use the standard deviation of a discrete random model so that we can talk about exactly how spread out the expected values are according to their probability. And this is the formula for it, but I don't ever want you to use that formula because we will never make this calculation by hand. If you're asked to find both the expected value and the standard deviation for a probability model, go to your calculator. Do this straight up in your calculator. It's the fastest way to do it. And you've already used this command. We're going to use the one variable stats command. So you use this command quite a bit in Unit 1. The only difference is that this is now a weighted average and a weighted standard deviation. So now we have a frequency list. So you want to put the x values into L1 and the probability values into L2. The list then will be L1 and the frequency list, the weights, will be L2. If you have an older calculator, you're going to put in the one variable stats command and then you're going to put parentheses L1 comma L2 and close the parentheses. The biggest mistake that students make with this is that they don't include the L2. They don't include the weight, and they're just taking the average then of the x values. But the x values all have different weights. We have to take that into consideration. So just to show you this on the calculator quick, so go to stat edit, put the x's in for L1 and the probabilities in for L2. And then go to stat calc one variable stats. And then calculate. So you can see that we've got an average here of $30 and a standard deviation of 140. This is a probability model, so we're using those Greek values. I forgot to say that on the last slide. So the standard deviation is the model. Notice that there's no S of X, which is what we used before in Unit 1 because we were looking at samples. This is a model, so we use those Greek letters. Unfortunately, your calculator gives X bar for all averages. But really, like this E of X, we can call it the expected value or the mean, mu, which is $30. And then the standard deviation, sigma, is 140. Another example. So there are 5,000 undergraduates registered at a certain college. Of them, 458 are taking one course, 645 are taking two courses, 568 are taking three courses, 1,864 are taking four courses, 1,357 are taking 5 courses, and 88 are taking 6 courses. Let X be the number of courses taken by a student, randomly sampled from this population. Create a probability distribution table for X and then calculate the expected value and the standard deviation. So, our possibilities for the number of courses. Well, nobody can take 0 courses, otherwise they're not going to technically be registered at the college. And it looks like nobody's taking more than 6. So the X values are going to be the 1, 2, 3, 4, 5, and 6. To calculate the probabilities, we're going to use just our definition of a probability and take the number of people who are taking 1 course and divide it by 5,000 to get that probability. And then we'll do that for each of the X values. Notice that the probabilities are all between 0 and 1. And if you were to add these together, which I did when I was creating this so I could check my work, when I added these together, I get exactly 1. So I have a valid probability table. I want to now calculate the expected value and the standard deviation. I'm not going to do this by hand. I'm going to use the calculator, and I'm going to go to put my X's in L1 and the probabilities into L2. And then we're going to use one var stats L1, L2. So again, we're going to have this as our command. Just don't forget to put that L2 into the frequency list. And we'll get an expected value of 3.6482 classes with a standard deviation of 1.3 classes. That's a pretty small standard deviation. Basically, we have an average of about 3.6 classes. One more example. A game costs $5 to play. You draw a card from a deck of cards. If you draw the ace of hearts, you win $100. For any other ace, you get $10, and for any other heart, you get $5. If you draw anything else, you lose. Find the expected winnings or losses for this game and the standard deviation for the distribution. So first we want to talk about the outcomes. We have 4 of them here. The ace of hearts, which means that we're winning the most money. Any other ace, any other heart, and then something else. And I've included a picture here of a deck of cards because I know not everybody is familiar with a full deck of cards. So a deck of cards has 13 cards for each suit. And we have 4 suits: diamonds, clubs, hearts, and spades. For each suit, there is an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a jack, queen, and king. This totals 52 cards, and again, we have 13 in each suit. So notice here that we have 4 aces. We only have 1 ace of hearts. So let's look at our outcomes. We can get the ace of hearts, another ace, another heart, or anything else. Remember, we have to include all of the possibilities that can happen with this game. Now we want to calculate the payout for each. If we draw an ace of hearts, we win $100, but you can't forget that you still paid $5 to play the game in the first place. So the payout is not $100, it's $95, because you're already down $5. If you get any other ace, you'll win $10, but again, you paid $5, which means that your payout is $5. For any other heart, you basically get your $5 back, which means that you haven't gained anything. And then if you get anything else, you lose, meaning that you're down that $5. Now we want to calculate the probability of each of these happening. There's only 1 ace of hearts. So again, there's a total of 52 cards. So the probability of getting the ace of hearts is 1 out of 52. There are 3 more aces. So 3 out of 52 would be the chance that you get some other ace. There are a total of 13 hearts, but the ace of hearts is included in the first outcome. So there's 12 hearts left over. So the probability that we would get any other heart would be 12 out of 52. And then finally getting anything else would basically be if I take 12 plus 3 plus 1, so 16, and subtract it from 52, there are 36 other ways that I can get a different card other than these cards listed. This will ensure that I have a valid probability table. So each probability is between 0 and 1, and they're going to add up to 1. Again, I want to find both the standard deviation or the expected value and the standard deviation, so I'm going to use my calculator, and I'm going to put x into L1 and the probability into L2, and we're going to use L1 as the list and L2 as the frequency list with the one variable stats command. When we do that, we get an expected value of negative 1.35 and a standard deviation of 13.8, which means that overall, if we play this game a lot, we should expect to lose $1.35, which doesn't sound like a lot. Maybe most people are okay with that. But the standard deviation is pretty high, 13.8, which means that there's going to be a large fluctuation in winnings to losses. Okay, in our next video, we'll talk about the binomial model.